So here is an indefinite integral for you to try to calculate. And on the next two slides, you have the solution with some comments and also a check of the answer by differentiating it to verify that one obtains the original integrand. So my suggestion is have a go with pen and paper and then come back. Welcome back. Let's go and look at the solution. Okay, so here is our integral, and when we look at it, I think it's fairly natural to use integration by parts. I don't see how anything like a substitution is going to help. So I think if you're going to use parts, it's very helpful, very good practice to write out the integration by parts formula. And then we have to decide what we are going to differentiate and what we are going to choose to integrate. And in this particular example, it doesn't really matter. You could choose to differentiate this and integrate this, or vice versa. And if you'd like to afterwards, you could attempt this the other way around. But what I'm going to do is I'm going to choose to differentiate the exponential factor. And to be honest with you, the real reason I'm doing that is because if I differentiate it, it's going to bring a factor of 2 in front, and were I to be integrating it, I would have factors of a half, and I just think this is likely to be a little bit simpler in terms of the algebra. It will still give you the same answer. So if we are differentiating the exponential function, we are going to be integrating the sine function, and the integral of the sine function is minus the cosine, because if you differentiate cosine you get minus sine, we want plus, so we put a minus sign in front. So now we have everything ready to go into this formula here. So our integral, that I'm just calling I for brevity, is u times v. So it's minus cosine of x times e to the 2x. And then we have minus the integral of 2e to the 2x. So I'm just going to put this 2 in front of the integral sign to make things look less scary. Leave the e to the 2x. And then we have to put in v, and v is minus the cosine of x. So there's a minus sign from the integration by parts formula. There's a minus sign from this. So overall we have plus. So our new integral is e to the 2x times the cosine. And what you might think is, well, this doesn't look like it's helping because we've got really exactly the same type of integral again. But what we can do is we can just try to do it again. And this is something that is quite often needed with integrals when you're using integration by parts and you have got trigonometric functions involved. Now, if we're going to do this, it's essential that the term we got from differentiation is differentiated again, and the term we got from integration is integrated again, because otherwise we would just go back to getting that this integral was equal to itself, which is true, but useless. So what we're going to do is we choose u is e to the 2x again. So we differentiate that just as above. And v prime is now the cosine of x, and that means its integral is the sine of x because the derivative of sine is cosine. So now we substitute this into this. So we just write out minus cosine of x e to the 2x plus 2, and now the 2 is going to multiply all the terms, or both the terms, in the integration by parts formula. So I think it's very good practice to open a big brackets, write out these terms, close the big brackets, and sort it out on the next slide. So u times v is e to the 2x times sine of x, that's here. And then we have minus the integral of u prime, which is 2e to the 2x, and I'll take the 2 outside of the integral. that's another 2, it's not the same one as here, it's from this bit, times e to the 2x, and then we have v, and v is just sine of x, and then we close our brackets. So now let's expand the brackets, bearing in mind the factor of 2 is here. So this is just as above. Here we have plus 2 e to the 2x sine of x, and then we have plus 2 times minus 2 is minus 4 times this integral. But this integral is our initial integral I. So in this example, what we see is that by using integration by parts, which changes one integral into some algebra and a different integral, what we've done is we've not reduced the integral to a trivial integral, but instead, or something we can calculate, but instead we've got that our integral is some algebra plus some number, here minus 4, times our original integral. So by using integration by parts twice, we have turned this definition into an algebraic equation for our integral. So I'm now going to bring this over to this side by adding 4i to both sides. We've got one of it here, so we've got 5i in total is equal to this term and this term. And now there is an ambiguity of an integration constant in this integral. Similarly, there's an ambiguity here. Once I've moved all of that ambiguity to this side, I think I shall put plus c to show that there is an ambiguity here. And now what I do is I just divide by 5. So this is our integral, this is what I was, is equal to minus 1/5, we just divide that by 5, times cos of x e to the 2x, plus 2/5 e to the 2x sine of x, plus, and in some sense it's this constant over 5, but I'm just going to essentially redefine what c is and just say it's plus an integration constant, whatever it is. So when we meet integration by parts, at first, in the first examples that we study, we normally use integration by parts to take an integral that we can't calculate and turn it into an integral that we can calculate. In examples like this, we use integration by parts to turn our integral into an equation relating our integral to algebra and our integral, and that just gives us the result for the integral. So it's very good practice to differentiate this result and see if we obtain the original integrand, and if we do that a lot, we will become very good at differentiation. So let's do that on the next slide. So this is the result that we obtained on the previous slide. And to check it, we're going to differentiate this and see if we obtain the integrand. Now, both of these terms have a factor of e to the 2x multiplying them. So I'm going to factorize these terms and write it as this times e to the 2x. That means we're going to be using the product rule. I mean, even if we didn't factorize, we'd still need the product rule for these products. And again, this is the way that I think people should write the product rule. So everything here is divided by 5. I'm going to take a factor of 1/5 outside, pull it through the derivative. So now we're left with this. This is our first term, the equivalent of u, and its derivative, if I differentiate minus the cosine, it gives us plus sine. And if I differentiate 2 times sine, I get plus 2 times the cosine, multiplied by e to the 2x. And then we have plus, and it's u, so this bracket is just repeated, times the derivative of e to the 2x, and from the chain rule that's going to be e to the 2x times the derivative of 2x, which is just a factor of 2. So now we expand the brackets here, and e to the 2x multiplies everything, So I'm going to pull it outside and just write it at the end. So it's 1/5, open brackets, sine of x plus 2 cos of x. We'll put that at the end outside. Minus, and now everything here is multiplied by 2. So it's minus 2 cos of x plus 2 times 2, 4 sine of x. Close big brackets, all multiplied by e to the 2x. And now when we look at this, we see that the 2 cosine of x and the minus 2 cosine of x cancel. And what we're left with is sine of x plus 4 sine of x, so that's 5 sine of x. And again, the 1/5 and the 5 factors cancel, and we are left with sine of x times e to the 2x. And that is our initial integrand, and that's exactly what we expected if our result was correct. So in this way, we have confidence that our result is right. And I think this is a very good habit for people who are studying calculus to get into. And with that, I'll stop this video.